Wait, who did wait for it?
I'm going like scared.
I understand.
I want to like understand class and like baseball.
But you were speaking of this part, but then when I went. Sure. That's what you have. No problem at all. So I got kind of filtered out. Okay, very good. But that serves you, give you what you needed. Thank you for doing it. Welcome. So, ladies and gentlemen, that in a nutshell is like the ending of our chapter. Now, tomorrow you will do a practice PSAT. So I'm not sure if we'll be, mentally exhausted or how we'll be feeling tomorrow. So I want to take a big step today so that a lot of tomorrow will be practicing problem solving. Okay, so we have gotten our way through the models of the atom. We're going to touch on some review questions just to make sure, and the basic design for now. So we haven't gotten the full picture, but we've worked our way up to probably how you view the atom or what you've learned up until this point. Today, we're going to dig into exactly what are those numbers in the element square on the periodic table. So I'll go ahead and remind you that on the back of the first page of your unit packet, there's a handy dandy periodic table. Because depending upon where you sit, you may or may not be able to clearly see the numbers on this periodic table or on the one in the back. So it's always good to have one to reference. That's why that's there. But if you want just another free one, not in the packet, they're over by the phenoid. You can pick a new one up every single day if you want. So we'll spend some time on this today and then get into the mole. But before we do, let's warm up with some questions. So in your packet, if we could find our way, and I know we didn't answer everything here, we will. Could we find page 9, please? Page 9. And on page 9, there are just 4 multiple choice. Let's take 2 minutes. I will tell you for number 1, I think there's a stronger choice, but a good, solid second choice. So hopefully you're narrowing it down to one of the 2. Okay, go. You good? Okay. Thirty more seconds. Okay, if I could interrupt you where you are. For number one, we're really looking for what speaks to matter cannot be created nor destroyed in chemical or physical changes. So A is true. Oh, that's not the choice. A is true. That communicated the very first part of the atomic theory is matter's made of atoms. And of course, oh my gosh, no, they can be destroyed. So the two possible are C and D. So it depends on where your thinking is. Dalton was trying to communicate that there's nothing smaller than an atom. We can't divide them, they don't disappear. And so maybe that, may seem like the stronger choice to you. Or just saying they don't disappear whenever in a chemical reaction we form things with a new chemical identity. They just rearrange and form different compounds. So it's not that they disappear or appear. They just create new things. They're just rearranging. And so I think we could make a good argument for C or D, truly. So in number two, but before we get to two, now, law of definite proportion. It's unfortunate that sometimes we'll see proportion and composition used simultaneously. But the key is definite. So this means the law of definite composition, that's what I'll always call it. That's what your book always calls it, but some other books will call it definite proportion. That is the mass ratio. That was Proust, the mass ratio. So D is the choice. Now, if it said multiple proportions, that is the number of atoms of each element. Okay, that was Dalton. So number two, is it talking about ratio of atoms or ratio of masses? That answer is what? So it's talking about they're combining, we're forming two different compounds. The ratio, Ben, of the mass. The mass. That's what Proust said gives identity to a compound, the ratio of mass. So B, definite composition. So actually 2 and 3 both address mass ratio. Okay. Now, if this read combine with a given atom ratio of 1 to 2, or if this said the law of molar proportions, it would be the same ratio of numbers of each element. So can we see the difference and the wording that'll come our way? Yes, no, maybe so. Wearing masks, that was a little uncomfortable, but necessary to keep us safe. Totally get it, totally get it. But oh my gosh, wasn't it sometimes it was just like hot and uncomfortable? But what I was bothered with the most is I couldn't see my students' faces. So I had a really hard time being able to judge, like, wait, do we get it? Do we not get it? I can't tell without the mask because we're not showing it. So you'll let me know if you're unclear. All right. So then number 4, atoms can never combine with any other atoms. No, he said they combine in whole number ratios, right? They must be divided, or they may be. No. He never said divided, rearranged. But he did say. So Sophia, can you choose an element? Great. And choose a number between 50 and 100. Great. So if you had 60 atoms of helium in your hand, every single one would be identical. Every single one, like they were all clones of each other. That's what they definitely thought. But we'll talk about that today. So any concerns? Yes.
So do we actually know which one for number one is the better answer? Didn't you
I
say
think
there
with
was
the-
one better answer?
It's more like the disappearing, but then when I started to just hear myself talk out loud, it seems like that also. So I think it's a tie. I think it's a tie. What do you think? Do you have a, yeah, oh my gosh, I would never have a question like that on the test that, yeah, or I would accept those two answers. Yes. D. So it's about definite proportion, definite composition is about ratio of masses or mass percentage. So that's the key. If this read the law of multiple proportions, then it would be C. Okay. All right. So yes, ma'am. A ratio of numbers. Go ahead. I get it very, very much. I get it 1,000,000% what you said. But it says the ratio of mass with another given mass. It just happens to be that they're like whole numbers. So it's telling you not the ratio of atoms of each element, it's the ratio of the masses. If it said like whole number ratio of elements or the atoms combine in a whole number ratio or the atoms combined in a ratio, and then they would give whole numbers. So mass is not referenced at all. Yeah, but if it's talking about, and because it's saying it's the relationship of mass of each element. Yeah, and it just so happens. So it must be like one is like 20 grams and the other is 40 grams. So it just boils down to that. But because it's a ratio of masses, yeah, that's why I wanted, to make sure that, yeah, we were comfortable with that. Because we may think like, oh, wait, but it's whole numbers, but it's talking about ratio of masses. So we left off with Rutherford's discovery. And so J.J. Thomson, Max, with a cathode ray tube experiment, discovered. Yeah, but what was the glowing line made of? Yes. Now, all that he found was evidence of these incredibly small little pieces, and that there must be something positive there because atoms were neutral, didn't know what was positive, so just said it was a cloud. So Rutherford tried to just get more evidence of that, but then by golly, found that it's not a positive cloud. It's an incredibly, incredibly crazy dense nucleus where the positive is. If I could just show us a quick visual. Oh, I'm so sorry. Probably. Sometimes I wish Zoom was a little something like this. Oh, shit. Sorry, that took me a moment to get. Okay, so there, but that is a gross overestimation of how the nucleus really is, but the nuclear model. Okay, can I just go back because I forgot that I actually found a photograph of plum pudding. Doesn't look very appetizing. So again, it's like a baked French toast with raisins, then they pour a plum sauce over it. But the whole point is, if you take a scoop of it, or if you take a piece of a chocolate chip cookie, in the case of the plum pudding, the baked bread is the positive sphere. And the randomly scattered electrons are represented with the raisins, where the chocolate chips, of course, are the electrons, and then the cookie is the positive spin. Okay. So Rutherford's experimentation, remember, he definitely thought he would just get more evidence that the atom was just this cloud of nothing. The alpha particles, it was predicted, would go straight through. The majority did, showing the majority of the atom is empty space. Some were deflected and some bounced back. So all of that, he concluded, it's not a positive cloud, it's an incredibly small positive nucleus. It was not until 8 years later. So 1910, 1911, the nucleus was discovered. And then 8 years later, we don't have to know this, Rutherford and his team discovered, oh, it's not just a positive chunk. That chunk is made of smaller things. And it's the things it's made out of that make it positive. The hardest and last subatomic particle, we don't have to know this, that was discovered was the neutron. Neutrons have no charge, so they were a little hard to detect. It's easier to detect things that are charged with magnetic fields and so on. But an interesting little tale, Chadwick, I guess he was a little shy. And he got in the wrong line when he was registering for classes in college. He wanted to study math. He was not in the math major line, was too embarrassed because he accidentally got in the physics major line. Started physics, really enjoyed it, became a research scientist, discovered the neutron. How about that? So maybe he was meant to, of course, not just study math. So interesting. We looked at this a little bit yesterday, but what I'd like us to enjoy is this head ed video. It's just a couple of minutes long. It is an animated cartoon. The animated narrator is an excellent chemistry teacher from Colorado. His name is James Bergman. And it just does an excellent job, really trying to give us examples to help our minds grasp how much of the atom is empty space and then the density of the nucleus. So it does a really, really good job. Oh, yeah, our sound is on. Sorry, the sound is a little scratchy, but we'll be all right. Okay, so enjoy. A couple minutes.
You probably already know that everything is made up of little tiny things called atoms. You might even know that each atom is made up of even smaller particles called protons, neutrons, and electrons. And you've probably heard that atoms are small. But I'll bet you haven't ever thought about how small atoms really are. Well, the answer is that they are really, really, really small. So you ask, just how small are atoms? To understand this, let's ask this question. How many atoms are in a grapefruit? Well, let's assume that the grapefruit is made up of only nitrogen atoms, which isn't at all true, but there are nitrogen atoms in the grapefruit. Well, to help you visualize this, let's blow up each of the atoms to the size of a blueberry. And then how big would the grapefruit have to be? It would have to be the same size of actually the Earth. That's crazy. You mean to say that if I filled the Earth with blueberries, I would have the same number of nitrogen atoms as a grapefruit? That's right. So how big is the atom? It's really, 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 really small. And you know what? It gets even more crazy. Let's now look inside of each atom. That's the blueberry, right? What do you see there? In the center of the atom is something called the nucleus, which contains protons and neutrons. And on the outside, you'll see electrons. So how big is the nucleus? Well, if atoms are like blueberries in the Earth, how big would the nucleus be? You might remember the old pictures of the atom from your science class, where you saw this tiny dot on the page with an arrow pointing to the nucleus. Well, those pictures, well, they're not drawn to scale, so they're kind of wrong. So how big is the nucleus? So if you popped open the blueberry and we're searching for the nucleus, you know what? It would be invisible. It's too small to see. Okay, let's blow up the atom, the blueberry, to the size of a house. So imagine a ball that is as tall as a two-story house. let's look for the nucleus in the center of the atom. And you know what? It would just barely be visible. So to get our minds wrapped around how big the nucleus is, we need to blow up the blueberry up to the size of a football stadium. So imagine a ball the size of a football stadium, right smack dab in the center of the atom, you would find the nucleus. And you could see it. It would be the size of a small marble. And there's more. If I haven't blown your mind by now, let's consider the atom some more. It contains protons, neutrons, and electrons. The protons and neutrons live inside of the nucleus and contain almost all of the mass of the atom. Way on the edge are the electrons. So if an atom is like a ball the size of a football stadium, with the nucleus in the center and the electrons on the edge, what is in between the nucleus and the electrons? Surprisingly, the answer is empty space. That's right, empty. Between the nucleus and the electrons, there are vast regions of empty space. Now, technically, there are some electromagnetic fields, but in terms of stuff, matter is empty. Remember, this vast region of empty space is inside the blueberry, which is inside the Earth, which really are the atoms in the grapefruit. Okay, one more thing, if I can even get more bizarre. Since virtually all of the mass of an atom is in the nucleus, now there is some amount of mass in the electrons, but most of it is in the nucleus. How dense is the nucleus? Well, the answer is crazy. The density of a typical nucleus is 4 times 10 to the 17th kilogram per meter cubed. But that's hard to visualize. Okay, I'll put it in English units. 2.5 times 10 to the 16th pounds per cubic feet. Okay, that's still kind of hard to figure. Okay, here's what I want you to do. Make a box that is 1 foot by 1 foot by 1 foot. Let's go and grab all of the nuclei from a typical car. Now, cars on average weigh 2 tons. How many cars and nuclei would you have to put in the box to have your 1 foot box have the same density of nucleus? Is it 1 car? 2? How about 100? Nope, nope, and nope. The answer is much bigger. It is 6.2 billion. That is almost equal to the number of people in the Earth. So everyone on the Earth owns their own car. They don't. We put all of those cars into your box. That would be about the density of nucleus. So I'm saying that if you took every car in the world and put it in your 1 foot box, we have the density of 1 nucleus. Okay, let's review. The atom is really, really, really small. Think atoms in a grapefruit, like blueberries. The nucleus is crazy small. Now look inside the blueberry and blow it up to the size of a football stadium. And now the nucleus is a marble in the middle. The atom is made up of vast regions of empty space. That's weird. The nucleus has a crazy high density. If you put all those cars in your 1 foot box. I think I'm tired.
Kind of is on the edge of maybe a little bit silly, but I really like, even when he kind of jumps in to the blueberry and tries to get to the nucleus. If you've been in PNC Park or what now the Acrisure Stadium, right? Usually we get like the peanut heaven seats if we go to a game or see a show or something. I can't imagine from those upper seats being able to see a marble on the middle of the Pirates field or the Steelers field and so on. That's what we're talking about, the amount of empty space. So that 1 foot by 1 foot by 1 foot box, that's like the common Amazon box. I mean, of course, we can order and get delivered larger things, but I think that's like the cost. I can't even imagine taking all of the student cars in the student parking lot and putting those all in the box, let alone all the cars in the world, let alone if everyone on Earth had a car and we put it into the box. Just mind blowing. Mind blowing. Have you, and we're not going to go down a political road in any way, shape, or form, or more road or anything. Have you seen photographs of Hiroshima or Nagasaki after the nuclear warheads were used? So what do you recall from those images? Yeah. Right. So, cities that had, pretty adequate multi-story buildings would just reduce to rubble. Anybody else? I think, and not to like, again, moral like discussion, because we could really have a good discussion for days on that. The amount of uranium in the first nuclear explosion could fit in the palm of your hand. Palm of your hand. And what caused the destruction in a nuclear warhead, the nuclei are open. Super heavy elements like radioactive uranium are allowed to rapidly decay. We actually throw neutrons at them, so their nuclei are already unstable. And we throw a neutron and one opens, that sets more neutrons that open more and more and more. It's a chain reaction. Think of the density of a nucleus. Those protons and neutrons are packed. And that shouldn't be. We know that like charges repel. Well, when the protons come so close, another force comes into existence, the nuclear force. That's what we wrote down that holds the nucleus together. That is what is unleashed in a nuclear explosion, but what is harnessed in nuclear power. So definitely, like the building destruction, if any human was a half a mile from the center of the explosion, they vaporize. That's hard for me to grasp. You know, whenever bodies are cremated, that is, I'm not sure what temperature, but definitely in the hundreds of Fahrenheit, if not the thousands of Fahrenheit. And there's still remnants of bone and so on left, but completely vaporized. So if you visit those cities, they have remnants of concrete where individuals were walking and the flash of energy scarred their shadows into the concrete or their footsteps and so on. So those are left there just in kind of memoriam. But that intense of energy is inside that nucleus. So amazing, amazing, amazing. Anything? Questions, comments? I have no idea what that gorilla was for. I think that was just comedic humor. I have no idea. If anyone noticed, there was like a cartoon gorilla. Anyway. So, can we turn to that page 14 in our packet? All right. So, we got some of this, and again, now the nuclear force, So, the strongest force that we interact with throughout our lives is really just electromagnetic, and that is, or electrostatic, opposite charges attracting. But this definitely is stronger. Okay, so atoms of the same element that have different masses are called. We'll get to this in a second specifically. Oh, anyone say aloud? You know this. We'll get to that. We'll get to that more. All right. Bennett, could you please choose an element? Any element.
Sorry.
I'm so sorry. I'm pretty sure I said any element. Okay. Okay. You said magnesium, correct? Okay. In the square of magnesium. Now, again, if you can't see adequately the numbers on the periodic table clearly, and again, there's one there, please reference the one in the back of your front page or grab another one. See, I know. So have yours handy or grab one. But yeah, my gosh, I make it available. Don't make it hard on yourself. Bennett, one more thing, sir. In the element block, now they're not always in the same place on all periodic tables, but you will absolutely, on the overwhelming majority of the periodic tables, and definitely on the ones I give you, you'll be given two numbers. One is a whole number, and for magnesium, what is that? Yep. And often that's in the top right, in the top left. Usually that's given in the top. On our periodic tables, it's in the front center. And then there's a number below, and that has values after the decimal point for the overwhelming majority of elements. So 24.305. Okay. The 12. Nick, do you know what the whole number is known as? It's okay if not. It is. But we don't call it the proton number. Yeah. So wherever the whole number might be, that is the atomic number. And Nick, you nailed it. The atomic number is, if you learned anything other than that, erase it. It is the number of protons. That is it, that is it, that is it, that is it, that is it. Not anything else. The number consistently of protons. That determines what element it is. So what makes magnesium magnesium is it has 12 protons. It could have 0 or 500 electrons. Now it wouldn't, but just saying. That doesn't change if it's magnesium. It could have 0 or 100 neutrons. It doesn't matter. That does not give it its identity. What determines its magnesium is the number of protons. So, Kyler, you're taking a walk in the woods and you stumble over an atom. You want to know what element it is. So you analyze it. It has 6 protons. What element? You got it. You got it. You got it. So, Jillian, you're taking a walk in the woods. Stumble over an atom. Want to know what element it is. And you analyze it. 72 protons. Now, can you pause just a second? Because I bet you know what that is if we forget the name of an element. Because we're really getting to know that. Just say its symbol. But also, I didn't ask you to learn what HF is. Just say its symbol. Which, do you know what the name of it is? It's okay if not. It's weird.
I don't know.
Hafnium. A little strange, I think. A little strange. All right. So the number of protons determine your element. Okay. This number. If the number that has digits after the decimal is rounded to a whole number. So of course, 24.305, we would round to 24. That number rounded to a whole number is mass number or atomic mass. We can use those interchangeably. If you keep it with decimal values up to the decimal, it's not that. So to a whole number, then it's called atomic mass or mass number. Okay. So the video reminded you, we talked about the mass of an atom comes from protons, neutrons, electrons. But the electrons are so tiny in their mass, we count them, but they don't impact the value. So really the mass is due to the protons and the neutrons. And the way that we as humans have devised the determining of these numbers, the proton is assigned a value of 1 and the neutrons are assigned a value of 1. So this 24 could be because of 10 protons and 14 neutrons. It could become it could be because of 14 neutrons and then 10 protons. But of course, to be magnesium, it has to have 12 protons. So then we know if the mass number is protons and neutrons, we subtract the atomic number, which is just protons, to get our number of neutrons. So an atom of magnesium would have 12 protons. It would have 12 neutrons. How do I find electrons? Yeah, do you know? Easy peasy. I bet you do. How do we get number of electrons? I think that'll give us neutrons. What charge do we assign to a proton? Yeah. What charge is a neutron? Yeah, no charge. An electron? Yeah. So if we know to be magnesium, we have 12 positives. There we go. But only in this chapter do we safely just trust that we're dealing with neutral atoms. Jackie, could you choose another element, please? Any element that you want. Sounds good. Yes, ma'am. No, go ahead.
Is it electrons or some number of protons or some number?
It's the same number of protons for now, but it's not always. We most often encounter elements in ion form, and we'll learn what that is and how to know the ion charge. Do not worry. And so I think some of us may come into this class calling atomic number the number of protons and that's just if we have neutral atoms. Okay, so carbon, Sabrina, to be carbon, how many protons? You got it. So then, Marcus, how many electrons? Yeah. Max, number of neutrons for carbon. How do you know? So, sir, instead of magnesium, let's do manganese. Okay, Max, manganese, an atom of manganese. How many protons? You got it. Now, if it is neutral, no charge, how many electrons? Yeah, because the number of electrons has to equal the number of protons. In the atom, where do we find all the mass? Yes, but where? Where's the mass of an atom? Where is it found? Yeah, what's the nucleus made out of? Yes, so that number rounded to a whole number, the number with values after the decimal place. So 55. If we round it to a whole number, that's protons and neutrons, each being assigned a value of 1. Well, I know to be manganese, it has 25 protons. How many neutrons? So is it always the same? No. It varies more and more and more further from 1 to 1 as we proceed through the periodic table, just to let us know that. So our numbers, protons, neutrons, electrons, for neutral atoms will be the same for a little while. Okay, questions? Dalton believed that all atoms of the same element were identical. Remember, I asked Sophia to choose an element. She chose helium. We said if we had 60, they would all be identical. Well, that's not exactly true. So I guess that is where we will pick up tomorrow. So could I ask you, minimal, could we please, on page 12, there's a list of names that we've addressed. A list of names. Can you, I don't know. Oh, well, that's nice. I should have erased that. This is letting you know how many times each name is used. I don't know if that helps or not. But for this statement, who did the experimentation that led to that, or the thought in the case of Democritus? So if you don't mind just associating, that should just take us maybe 5 minutes, maybe. Okay, so something that we've learned about the atom over the last couple of days. Adelaide, something new that you know about atoms. Or we're reminded of, because maybe none of this is new for you. Very good, very good, very good. And Cameron, can you share something that you were either reminded of or you learned? Very good, very good. All right, any questions, ladies and gentlemen? Yes. Could I please? Am I? So how about this? My next class is, all the seats in that back row are empty. So after you do that, and check in, how about check in with your study hall teacher? When you come in, I'll have the rest of the common section on one of the desks. Can I keep you? Perfect. Hey.
You got Miss Gerhart. I'll put it right here.
Fantastic. Thank you so much. Okay, so you're welcome. And do you want to go check in with your study hall teacher first? Or good?
I'm sure it's fine.
Perfect. And you don't need that like English metric unless you want me to give it to you just so you feel comfortable.
Do I?
No.
Okay.
I wouldn't,
Wait, no.
but here are your equations, and I'm so
Okay.
sorry, I forgot to write that in the problem.
Okay.
Okay.
Yeah.
If you don't have enough room for the first one, I should have given you more room.
Okay.
Please feel free.
I need a voice three, right? Backwards.
That would be great.